Okay, welcome to Thursday's lecture. In the last lecture, I went over the chain rule and a few other problems, super important, but I started talking about logarithms when it occurred to me that I hadn't really given you all the tools. We had gotten as far as the derivative of natural log is 1 over x, and then sometimes you have to use the chain rule. But also there's tons of rules for logarithms which are super helpful, and they are here the properties of logarithms in section 11.1, and these are things that you really have to memorize. You have to know them and understand them. So for example, that first rule says, let's do everything in natural log. These are the same rules. It's just that over here, these are base A, which means any base, whereas over here they've just chosen E as the base. So the rules are exactly the same, but this is a very specific example where E is the base. So if we took natural log of e to the x, what this says is, remember this means log base e of e to the x. What this means is, what number do you have to raise e to in order to get e to the x? I'll write that. What number do we have to raise e to in order to get e to the x? Well, the answer is x, obviously. So this is just equal to x. In other words, what this shows you is that natural log undoes the exponent function. So natural log of e to the x just gives you x. It'd be the same thing as saying, what is x minus 3 plus 3? Well, it's x, right? Because the minus 3 undid the plus 3. The second one it says is e to the power of natural log of x. Now this says, remember what this means is e to some number gives you x. Now you raise e to that number, well, it better give you x. So in other words, rules 1 and 2 are really kind of the same rule. Basically, it's saying natural log undoes e and gives you x, and e undoes natural log and once again gives you x. Now 3 is where the rule 3 is actually where the real meat is here in the rules. It says natural log of the product of two numbers or two functions or whatever is the same as the sum of the natural logs of them respectively. And an example would be, type in your calculator natural log of 35, and then figure out natural log of, because 35 is the same as 7 times 5. So now try the natural log of 7 plus the natural log of 5, and those better be the same thing. The fourth rule is really not a different rule. It's the same rule. It says that natural log of m over n is the natural log of m minus the natural log of n. And you say, well, how is that the same rule? Well, because multiplication and division are the same. It's that like if you, for example, if you want to take 3 divided by 2, this is the same thing as 3 times the reciprocal of 2. 3 times 1/2. I mean, so, multiplication and division, okay, so they're not the same exactly, but there is a way to make them similar. So in this case, you multiply by the reciprocal. So the same here. The natural log of mn is the natural log of m plus natural log of n. Well, now if you divide n instead, all that happens is this becomes a minus. That's it. And then the last rule, super important, is natural log of m to the power of p, where p is an exponent, is equal to, you can bring the p out in front as a coefficient, and that becomes p times the natural log of m. And an example of that would be, let's take the natural log of 8. Well, 8 is the same thing as 2 cubed, so this is natural log of 2 cubed. So this should be the same thing as 3 times the natural log of 2. So do in your calculator natural log of 8, get a number, and then do 3 natural log of 2 and make sure that those are the same number. And then finally, the other thing which I actually did mention last time, but I didn't realize that it was going to be the next page in the book, was this rule about, let's see, where the heck did I put it? It's this rule that says, if you have some log base a of x, it's the same as, well, it's the same as the log base anything, I'll say n, of x over the log base n of a. And if you choose n to be e, the 2.71 whatever, then what this means right here is natural log. So this becomes natural log of x over natural log of a. And again, the reason this is useful is because your calculator does not have log base a. Doesn't have it. It only has either natural log or log, log, which is implied to be log base 10. Okay, so now we've covered ooh, here's a proof that the derivative of natural log is 1 over x. I have never seen this before, and it might be interesting to read. All right, so now we're just going to do exponents. But the good news about this is that, excuse me, is that we already started doing this before. I've already introduced you to the e function. We already know, excuse me, it's at the bottom of section 11.2, it says the derivative of e to the x is e to the x. And then if there's anything different, if it's not just e to the x, then use the chain rule. And that's what this next equation on my book 711 says. So an example, let's see, they have an example here of example 2a is f of x is equal to e to the 4x cubed. Now e is being raised to the power of 4 times x cubed. The derivative of that is just going to be this value times the derivative of what's inside there. So just be e to the 4x cubed times the derivative of this. Using the power rule, I get 12x squared. And that is right there. That's the solution. And then there are several other examples. One of the examples uses the product rule. So it's an application of this using the product rule. You have 3t times e to something. And then the second one is going to be using, it looks like the quotient rule. It's w divided by e to the something. Finding the derivatives of those. And those are listed right here. They're very clear. And all of this, keep in mind, is nothing more than application of the product rule, product and quotient rule, the power rule, and the chain rule. And the only thing we've added in this lecture and the last lecture are e and natural log. And they're easy, because remember, the derivative of e to the x is e to the x, and the derivative of natural log is 1 over x. So that's the only thing we've really added in these last two sections. So now whenever you have, you start combining stuff, so natural log of 3x squared, well, it's the same as we did before, but now we've got the chain and the power rule. So now we've got, this is 1 over this, and then times the derivative of this, which gives me 6x over 3x squared. The 6 cancels with the 3 and becomes a 2. And then one of these x's cancels, and it gives me 2 over x. Just so you know, actually this is kind of important, I kind of glossed over this. This is what e to the x looks like. This is what's called an exponentially increasing function. This is, if you read that most recent Dan Brown book, this is the famous population growth curve, because it's been exponentially increasing since about, I don't know, since 1820 or something like that. And so it turns out, but to give you an example, if we want to find these points, if we want to plot them, if we plot, we're doing y is equal to e to the x. If we want to know at 0, so if we plug in 0 for here, we get e to the 0, that's 1, which means that one of those points is 0, 1. So right here, you can see 0, 1 is one of the points. If we go to 1, so y is equal to e to the 1, that's 2.7 something. So notice when we go to 1, we're up at e, which is about 2.7 something. But notice also when we go negative, e to a negative number is never negative. E to a negative number, if we have y equals e to the minus 1, that's 1 over e to the 1. And that's going to be like, I don't know, 0.3 something, I don't know. And notice that when we go to minus 1, we're still above 0. And no matter how far negative x gets, this curve will never reach 0 and will never become negative. So it asymptotically approaches 0. I don't know why there's two, oh, I do know why there's two graphs. Okay. So this one right here, this is e to the x. What it's showing you on this right graph is, notice it's drawing a whole bunch of tangent lines at various points, and of course you should know by now a tangent line represents the slope at that point, which means the derivative at that point. So what it's showing you is the derivative at each of these points, and I guess it's trying to prove to you that the derivative of the function at point 1 is e, and so forth. I don't think it's that helpful. Okay, this is actually potentially useful, and that is, well, what if we're not dealing with e to the x? What if we're dealing with something else, like 4 to the x? Oh, in fact, there's the example right there. So if you want to find, for example, so if our function is f of x equals 4 to the x, and we want to find the derivative of that, we treat it like e to the x, with one exception. We have to multiply it by the natural log of 4. So in other words, the derivative of this is just 4 to the x, but then we have to multiply this thing by natural log of 4. That's the only rule. Okay, that's exponential functions. All right, so we're at 15 minutes right now. I want to start talking about, let's go back now to 9, and keep in mind up until now, what we've done are the power rule, the product and quotient rule, the chain rule, and exponents and logarithms. And I've written them as e in natural log, but really broadly it's just exponential and logarithmic functions. And I think that's all you're going to need in terms of functions for this course. I think the rest of it is going to be, I hope the rest of it's going to be actual applications. So let's go back to section 9.9. And by the way, your homework so far is going to be section 11.1 and now 11.2, which we just did. Those problems are in D2L. Now we're going to go back to section 9.9. This is actually where the stuff gets useful to you, in terms of business and economics and accounting and all that sort of stuff that you're going to end up doing. So we've got example 1. So in section 9.9, we jump in and we start doing these things called revenue and marginal revenue, and then also there's cost, and then there's going to be marginal cost. Basically, here's what it comes down to. We already did some problems where, remember the pencil making machine was $9,000, but then the marginal cost for each pencil was 1.5 cents, and so we got a cost equation, which was that plus the number of pencils made. So this is a cost equation, and this is linear. What this means is, well, it's a line. So if we drew this, basically, what our cost would be, it would start out at $9,000. And then here's the number of pencils we make, and then it would be a line. Well, you can't really go back in time. There's no such thing as a negative pencil. It starts at 0 pencils, and it would increase with the number of pencils. That's all this means. So 0 pencils cost you $9,000 because you have to buy the stupid machine. 1 pencil is going to cost you $9,000 and 1.5 cents, and so forth. And then once you start getting out here, you make 1,000,000 pencils. Now you can figure out what your cost is. So your cost for 1,000,000 pencils is you put in 1,000,000 into X, and you're going to get, we got to move this decimal place over. 1, 2, 3, 4, 5, 6. It's $15,000. So 1,000,000 pencils is going to cost you that $9,000 for the machine, plus another $15,000 for those 1,000,000 pencils, is $24,000 for the 1,000,000 pencils. And so forth. Anyway, my point is, what we've already done this. Except what we did until now was only linear. That's it. And now the only thing we're adding in section 9.9 is these cost equations might not be linear. That's all. They may be other functions. So if you wanted to find out for this equation, 9,000 plus a penny and a half per pencil is your cost function. If you wanted to know what is the marginal cost of a pencil, the marginal cost means the cost for one more pencil. Well, you instantly know it's a penny and a half, right? But the way you can do that is to take the slope of this thing, or take the derivative. So the derivative of the cost function gives you marginal cost, and it's just equal to, the derivative of a constant is 0, and the derivative of this is 0.015. So what this tells you is that the marginal cost, the cost for one more pencil, is the first derivative of the cost function, and that gives you a penny and a half. Well, the same logic applies with any other function. I think it's really that simple. So the example they give you in 99 is they give you just some random cost function which is equal to 0.00001 x cubed minus 0.3 x squared plus 32x plus 2500. And we want to know, it asks you, what is the marginal cost function and what does it tell us about how costs are changing? Well, the marginal cost function is just the first derivative. So it would be 0.003 x squared minus 0.6x plus 32, and that goes away. So that's the cost, the marginal cost function. Notice before the margin, when it's linear, the marginal cost function is a number. There's no variability on x, which means it doesn't matter how many pencils we produce, the next pencil is always a penny and a half. But in real life, that's not true, often. Because, for example, a great example would be, if you're a small business, you know, you have to, I don't know what it makes to take pencils, I guess wood and graphite and a few other things. If you're a small business, your costs are higher because, you know, I don't think I need to explain that. As a small business, you have to, you're ordering smaller amounts, and so your costs are a little bit higher. So maybe as a small business, your cost is a penny and a half to make those pencils. But instead of making 1 million pencils, maybe now when you make 10 million pencils, your marginal cost is less because people, the timber manufacturers, I guess you don't really manufacture timber, but the people selling you the wood give you a break. They give you a deal. So when you make 10 million pencils, maybe it only costs you a penny to make each additional pencil. In other words, sometimes the marginal cost is not fixed, but it depends on the number that you make. And so in this example that they give you, indeed, the marginal cost is not a constant. It depends on how many you made. So then they ask you, well, what does it say about how costs are changing when x equals 80? So just put in 80 for this number, and I don't have access to my calculator because it's filming me right now, and I'm not going to try to do this in my head. But what this tells you, whenever you put this in your calculator, is this will tell you approximately your marginal cost. In other words, your cost of one more, I think they're selling blenders here, the cost of one more blender once you've already made 80. And then they ask you to do the same thing for 200. What is the marginal cost function at 200? So you would put in 200 squared minus 0.6 times 200 plus 32, and you will get different numbers for these. I'm hoping, I'm trying to glance at this and figure this out, which one is going to be bigger. It looks like this one's going to be bigger, which seems weird. It would seem like the more blenders you make, the lower your cost would be, but apparently in this function, it's just the opposite. But I could be doing that wrong. Just do this in your calculator, find out what these two values are, and that tells you approximately what the marginal cost of each of them is when you make 80 blenders versus when you make 200 blenders. So, okay, good. So that's marginal revenue function. Now, another thing about marginal revenue is this. Let me do something relatively simple because again, I don't have my calculator. I'm filming with it. So let's say there was some cost function that's just x squared plus 2x plus 1. So the marginal cost function is the first derivative, and it's 2x plus 2, right? Power rule. What that tells me is that the change in the cost depends on the number that I have produced. So, so let's say I want to know what is my marginal cost at I've produced 100, right? So then let's put in 100 here. So that would give me 2 times 100 plus 2 is 202. So what it tells me is that the marginal cost to make one more when I'm at 100 should be about $202. According to this. But if you remember, now what I'm about to say is going to require some brain power. The derivative was found by taking the slope of a point. In other words, when we took, actually it's the slope of 2 points, but they get real close together, so close together that they're essentially 1 point. Which means this may not actually be the marginal cost. It's going to be close, but let's find out what the actual marginal cost is. And the way we do that is, remember, marginal cost is the cost of one more. So the way I can do this, the way I can actually figure this out, is by figuring out what is the cost of 101 of these widgets, and then subtract from it the cost of 100 widgets, and that will tell me how much that 101st widget costs. That will be the actual number. Oh, crap. All right. Why did I choose 101? Oh, this is... All right. Let's see if I can do this. All right. So let's put these numbers back in. So that means 101 squared plus 2 times 101 plus 1. And I'm going to subtract from that the value when I put in 100. So that's 100 squared plus 2 times 100 plus 1. All right. 101 squared is going to be, it's going to be 10,000 plus 200 plus 1. Then plus 202, and then plus 1. Subtract off the quantity, 10,000, plus 200, plus 1. All right, I think I almost did it. So these go away, these go away, and these go away, leaving me with 203. You'll notice that this is not the same number as what I calculated before. It's close. This was a really good estimate, but it wasn't quite right. And so this is an important lesson. What this tells you is that the marginal cost function, which is the first derivative of the cost function, is a great estimate for the, sorry about this terrible handwriting, for the marginal cost, or the cost of one more. Now the reason, so why would you ever estimate? Why don't you just do it correctly? You want to know what the marginal cost is at 100? If you want to know what the marginal cost is at 100, just simply calculate the cost of creating 101 and subtract off the cost of creating 100, and it'll give you the actual answer. Why wouldn't you do that? Because if you're running spreadsheets and calculations for tons of different products and different time periods and whatever, you don't want to do this 5,000 times or 500 or even, 50 times. It would be way easier just to simply take the first derivative, get your marginal cost function, and it's a really darn good estimate of what the marginal cost actually is. And for all intents and purposes, these are the same number. I mean, they only differ by, 0.5%. So these are really good, but it's important for you to understand the difference between these two. So I think that is where I'm going to end it for now. I've covered a huge amount of material in this. So for this reason, I'm going to call it quits here. Your homework, do as much of 9.9 homework as you can. In fact, I've looked at it, so you should be able to do all of it right now. So at this point, you've got homework for 11.1, 11.2, and 9.9, and this is all due on Tuesday, and we'll discuss it then.